Perfect. Thank you.
So I've been, as Swathi mentioned, I've been studying or teaching, doing something in Vedic mathematics on and off for the last 12, 13 years now. Initially started off like everybody else with the interest in this techniques around, doing calculations easier, etc. But I always used to have this argument with a few friends as to whether is this just a system of speed mathematics, or is there something beyond beyond just the speed mathematics in there. And my understanding over the years is that it can potentially it's probably a very summarized system of arithmetic to start with, if and then applications in other fields, as probably a lot of you know. While Swamiji's sutras are probably not as exhaustive as Panini's grammar sutras in terms of the construct and the comprehensiveness, but what he has done in those sutras is an abstraction of the processes used in arithmetic, and they really do live by the definition of a sutra. Now, if you go back to Sanskrit literature and look at the definition of what a sutra is, it says alpaksharam asandigdham saravat vishvato mukham astobham anavadyancha sutram sutra vido. 6 characteristics of sutra. Alpaksharam, minimal syllables in the sutra. Asandigdham, no confusion. Saravat, it has to say everything that is needed to say in that given context. Vishvato mukham, applicable anywhere. Astobham, no redundancies or unwanted syllables. Anavadyam is error-free. Now, in modern IT terminology, I think this is like a microservice. Sutra is a microservice which can be applied or called upon by other programs anywhere when they come across that particular context. Panini's grammar sutras are also also follow this thing, and any sutra you look at Sanskrit text exhibits these characteristics. Now even Swamiji's the 16 sutras do exhibit that characteristics, and that's what I would like to bring out today, that they are really an abstraction of arithmetic process. While normally we use it in the decimal number system, but the same processes, without any change to the process, or without any change to the sutra, as it is, can be applied to all the number systems you can think of, and potentially also abstract an algebraic kind of definition of a given arithmetic process based on the sutras. So that's what I would like to do today, and show you that these sutras, even though they're very pithy, they're very small and easy to remember, actually pack an abstraction and a very thorough understanding of how the number system works itself, and how the place value system itself works. Those of you who've done Vedic mathematics calculation will understand that the entire process is very well structured around the understanding of the place value system, and that's what we will leverage to show various examples today. I will be working through along with you a few sums, so you'll have to bear with me toggling between this slide and a whiteboard as I work through some of the examples. So let's start with one of the most basic and probably the first sutra which we teach when we open a Vedic maths session, called the Nihilam Supra. Nihilam Navataha Charamam Dashataha. Simply means all from 9, last from 10. And we all know we use it in the context of subtracting numbers from powers of 10. Like, if you want to subtract a number from 10, 100, 1000, 10,000, etc., it's a very handy rule. In fact, if you look at how we subtract numbers, that's what we do. We strike out, carry forward numbers. After you notice what's happening, after we do all the strikeouts we have to do when we subtract a number from 100, That's exactly what we're doing. We're subtracting all the numbers from the left, each digit from the left from 9, and the last digit is being subtracted from 10. So that's the that's the rule. That's how the rule was formed. And it's once you know this, it's very easy to apply it. 100 minus 23 or any number, 100 minus 54. Very easily you can say 9 minus 5, 4, 10 minus 4, 6. Like that, you can take any number, 1,000, 10,000. All we have to do is go from the left, each digit we subtract from 9, and the last digit we subtract from 10. So if I'm doing a 3-digit number from 1,000, I go 9 minus like 342, 9 minus 3, 9 minus 4, and 10 minus 2, and I arrive at 6, 5, and 8. 6. Now this actually is a very powerful abstraction of the process of subtraction itself. That's exactly what we do in all the subtractions. Now, if we then try and apply it to other number systems, yeah, we all know a number system is starting from the right. They go in powers of 10 for a decimal system. So in fact, in Sanskrit, the names of the numbers are from right to left. Ankanam vamato mukhaha. So if you say 108, ashtottara shatam. Ashta is the rightmost, 8, uttara shatam. And there is 100 before it. So 108. So like that, the naming convention for numbers that's generally used in Sanskrit follows the rule from we name it from the right to left. And that's the number system that's been an invention of the Indian mathematics and contribution to the world of mathematics, right? So now, changing a number system is basically changing the number of digits I have to play with. So in a decimal system, we have 10 digits. In a quinary system, for example, we have only 5 digits. So 0, 1, 2, 3, 4, and the next number is 1, 0 again. So 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and then we get 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, etc. So we only have 4 digits to play with. And we would have, most of us on this call know, the powers go from power 0 on the right most and increasing power of the number of digits. If it's a decimal system, it is 10 power 0, 10 power 1, 10 power 2, etc. If it's a quinary system with 5 digits, it's 5 power 0, 5 power 1, 5 power 2, etc. So each place has the power moves. The power is a power of the number of digits. So 1, 2, 3, if I write in a quinary system, we all know that if we expand it, it becomes 38 in decimal system because it's 1 in the place of 25, 2 in the place of 5s, that is 2 5s are 10, and 3 in the place of 1. So that's what is happening. So now if I use this construct and try and do a subtraction, let's say if I was taking, I'm now working on, let's remember that we are working on quinary. So we have only 5 digits. So I have 100. And from 100, I'm trying to subtract 2 and 3 in quinary. This is all in quinary. Now, if I do a subtraction, like I do in decimal, this becomes 1, 0. Then I strike it out. Now, 1, 0 in quinary, in the quinary digit, the numbers are 0, 1, 2, 3, 4. And after 4, it is 1, 0. So the one number before 1, 0 is 4. So I have to put 4 here. And this becomes 1, 0. This 1, 0 in my decimal language is actually 5. So now if I do the subtraction, 5 minus 3, 2, and 4 minus 2. So if you have seen, if you can guess now what is happening, if I take another number, 100, and put 1, 4 under subtraction, and I strike out, this becomes a 4, and this actually becomes a 5. Then I get 3 and 1. So if I If I now go back and compare with my rule, what I had in Nihilam in the previous slide, all from 9, last from 10, that it's very easy to see that's becoming all from 4, last from 5 for a quinary system. So we have the Nihilam Navataha Charamam Dashataha being applied. It's exactly the same. Dashataha in a quinary system, Dasha in a quinary system is actually 5 in the language of decimal system. Nava is 1 less than Dasha is 4 if you convert from quinary to decimal language. So the rule is applicable. We just have to replace 9 and 10 with the equivalent in the number system we are dealing with, that's 4 and 5. And once you know that, then subtraction of any quinary number from quinaries of 1 0 1 0 0 1 0 0 0 etc. becomes very easy. Like in the decimal system, all we have to do is just change it with all from 4 and last from 5. In Vedic maths, we also call the resultant numbers as complements, right? 10, numbers adding to 10, for example, 2 and 8 are called complements. Numbers adding to 100, let's say 45 and 55 are complements. So to find a complement, we are subtracting from a 10 or 100 or 1,000 based on number of digits we have in the given number. So the job of finding complements, which is very handy in a lot of processes, as we will see, becomes the same in any number system. So if I am, for example, dealing with hexadecimal system, now it's easy to guess that the rule actually becomes all from 15, last from 16. So once you have worked out for one number system, you can see that it's consistent across all number systems. So if I am subtracting 2a, for example, from 100 in a hexadecimal system, all I have to do is just go all from 15, last from 16. So the 2 here I am subtracting from 15, that becomes 13 or D. And the A I am subtracting from 16. A is actually 10. So 16 minus 10 is 6. That becomes D6. So the complement of 2A in the hexadecimal system is D6. Now you can just look at it and tell the answer once you know that you are applying the Nihilam Sutra, and that's the easiest way to solve that problem. So this is to me, this was when I understood that this is how you apply, there is great joy in understanding, in figuring out that these complements in any number system can come with the same Nihilam Sutra which we use for the decimal system. That's one application. We will move on. Now in Swamiji's book, there is also a concept of vinculums, the bar numbers, right? So whenever I have and it's very useful, the bar number concept is very useful for, doing especially additions and subtractions. If you are not afraid of negative digits, handling negative digits. Now it's again a very powerful understanding of the number system, that the number system is founded upon the place value system. Each place, the digit is sitting in a place, and the place value is very important. Now, nobody said the digit cannot be negative. That's what the concept uses. For 28, for example, is 2 into 10 plus 8. And 28 can also come as 3 into 10 minus 2. That's also 28. So that's what we represent as 3 minus 3 bar 2 with a bar on top of the 2. Now this simplifies addition. Now if we can, in addition, if we can quickly replace the big digits with vinculums, suddenly the additions become very easy. Now the same thing can be achieved in other number systems as well. Exactly the same process of converting 28 to 3 minus 2. It's actually, you can see 20 plus 8 or 30 minus 2. Same thing you could do to a 2-4, for example, in quinary system, and it becomes 3 bar 1. Now there is a very easy way to calculate that, to find that. It's basically taking the complement of this digit. The 2 is the complement of 8. and then put a bar on top and increase the previous number by 1. That's what happened. It's exactly the same process. We don't have to think much. Take the complement of 4 is 1 in quinary system. The complement of 4 in quinary is 5 minus 4, 1. And then you are adding 1 to the 2 in the front. It becomes 3 bar 1. So again, exactly the same process of converting the form of the number. It's like writing a code for 28. Instead of 28, I'm writing as 3 bar 2 with the understanding that bar 2 means a negative digit in the units place. Similarly, in quinary system, 2, 4, I can write as 3 bar 1. Again, dealing with 3 and 1 is easier than dealing with a 4 when you're doing some calculation. So, and hence the benefit of writing in this form. But the process, if you notice, is exactly the same. Even if you're dealing with hexadecimal and you want to find a vernaculum form in the hexadecimal, all you have to do is take the complement of the digit you want to replace, and the digit on the left you add 1 to it. So the process is exactly the same. I wanted to bring this up because I'll use it later in a calculation. Another very fundamental thing I really like within the Vedic maths system is the process called Shuddha process for addition. Now, the way this works, if, for example, if I'm trying to do an addition like 87 plus 45 and 96, so when I'm doing this, what we do in Shuddha is at every stage, whenever I cross a 10, I carry forward at that step itself instead of going through the addition. Instead of going through 7 plus 5, 12 plus 6, 18, I will just go 7 plus 5, 12, which means I only carry 2 to the next step in the addition and I drop a 1 next to 4. And 2 plus 6 then becomes 8. And then I come back and pick up that 8 later when I do the next column. Now 8 plus 5 is 13. Again, I can drop 1 and I will take only a 3 to the next step. And 3 plus 9 is 12. I write 1 there and 2. And then I come back and pick up those two numbers. It becomes 228. This is how the Shuddha process works. Now, this is this process is really helpful when we add numbers in other digits. When we add numbers in other number systems. Now, each time we come across 1, 0, we cross 1, 0, we drop the 1 at that step and move forward. For example, if I go to base 5 and I'm trying to add numbers in base 5, let's say 2, 3, 1, 2, and 3, 1. So let's say I'm adding, these are all base 5. You have to remember we are dealing in base 5, 2, 3, 1, 2, and 3, 1. So I'm adding them in base 5. Now 3 plus 2 in the language of quinary is 1, 0. So I drop 1 next to it and 0 here. And 0 plus 1 is 1. Now 2 plus 2 is 4, no problem. 4 plus 3 is 7. 7 is 2 after 5. So it becomes 1 and 2. So this sum here is in base 5 directly. So what we have done is we have taken the Shuddha process and we have applied it in the quinary system, and we've been able to add the numbers directly in the quinary system without having to convert them into a decimal number. I mean, the way I've learned it at school, at least, is you convert each of those to a decimal system. Let's say 2, 3 in quinary is 2 into 5 plus 3. It becomes 13. Like that, I add everything to the total and then go back and then start dividing with 5 to get the quinary equivalent, right? So instead of doing that, what we are seeing here is we can directly do the math or the addition in quinary system, as long as we remember the Shuddha, the process of purification is whenever I reach 1, 0, I drop the 1 next and then move forward and carry forward only the remaining to the next step. So that way I'm actually adding the numbers in that respective number system rather than converting and adding. That's a very, I find it's a very nice application of the understanding of the number systems. Same in binary, for example, if you like 1, 1, 1, 1, 1, 0, 0, 1. So all you need to do is this 1 and 1 become 1 and 0. So you drop 1 and take 0 to the next step. So 0, 0, 0, 1. So I actually have a 1 in the units place in the answer. And for the tens place, we have to remember we dropped 1, 1. So then 1, 1, it's already 1, 0. And then there is a hundreds 1. So like that, you can keep adding. So now 0 plus 1 is 1, 1 plus 1, there is 1 goes to the left again. There is a 0, 0 plus 0 is 0. Then I have two ones there. Those two become 1 and 0. So that's how you get 1, 0, 0, 1, which is the total of that. So what we have done is we have directly adding with a little bit of attention to the numbers, we can directly add those numbers in the respective number system than having to go back and forth between decimal and that number system. Now it works for all number systems. Same process, as long as we remember that whenever we hit 1, 0, carry forward and move on. Digital roots. I'm just moving to the next topic. Digital roots, again, one of my favorites from the Vedic maths. It's in arithmetic also. We have something called modulo 9, which is very similar. Now, basically, digital root is a name given to a bijank, as it's called in Sanskrit. It's a name given to the remainder after dividing a number by 9. For example, 23, you divide by 9, it gives remainder 5. So 5 is called the digital root of the given number 23. Now there is a very easy process to find digital root. It's just adding the sum of the digits until you get a single digit number. So you keep adding the sum of the digits until you get a single digit number, you will get the digital root. That is one way, or a much more easier way is just cancel out all the 9s. Or digits adding to 9 in the number, what you are left with is the digital root. So for example, 631, all I do is cancel 6 and 3 because 6 and 3 are adding to 9. I'm looking for a reminder for division by 9. It only works with 9. So I cancel out 6 and 9, and then I'm left with 1. 1 is the digital root. If I do 6,312, again 6 and 3 add to 9. I cancel out 6 and 3. I'm left with 1 and 2, add them, you get 3. So 3 is the digital root or the remainder of division of 6,312 by 9. Now the digital root also works in all number systems. For example, in the quinary system, it is the remainder of dividing the given number by 4. In quinary, the equivalent of 9 for decimal is 4. Like as we saw when we were working through the subtraction. So the equivalent number here is 4. So the digital root in a quinary system is the remainder of dividing a given number by 4. The division, everything you need to do in quinary to get the actual result. But in case we are only looking for remainder of 4, all we need to do is cancel out 4s in the number, in the given number, or digits adding to 4, and then add the remaining digits. What we get is the digital root or the remainder of division by 4. So 2 and 3, for example, in 2 and 3, there is 1, 4 and 1, 1. So the 1 is the digital root. So 1 is the digital root of the number 2, 3 in quinary system. When divided by 4 in quinary, the remainder is 1 in quinary system. Similarly, 1, 3, 2. Now there is a 4 and a 2 in the total. So you exclude the 4 with 1 and 3 adds to 4. You cancel them out. What you are left is 2. So that is the digital root, or the remainder of dividing 132 in quinary by 4. That's the extension of the digital root. Now in a hexadecimal system, it is the remainder of dividing the given number by 15. In a binary system, for example, it's the remainder of dividing the number by 1. So you will get the same number which you have as the digital root, right? So it's a very powerful tool to get the remainder of dividing by the last digit in your number of digits you have. Now in a decimal system it is 9, in a binary system it is divided by 1, in a quinary it is division by 4, in a hexadecimal system it is division by 15. But the beauty is the process is exactly the same. Whatever is the last digit in your number system, you just basically cancel out that number and any number adding to that, any numbers adding to that particular number, and whatever is left, you add them, you get the remainder of dividing by the n minus 1th number in your number system. It's a very powerful way, and it is used for, you can also use it for validating our multiplications, etc. We will look at that when we do a multiplication. Now, before I would also like to show multiplications and divisions in quinary. Now, before we go there, it's useful to build multiplication tables in the number system in which we are working. Just a small table like this. For example, if I'm working on quinary, if I can have this small multiplication table, if you're not comfortable with additions, you can also do a small addition table. What is 2 plus 2? What is 2 plus 3, etc. Addition table is much more easier to fill out because you're only adding 1 at each in each cell. But the multiplication table becomes very handy when we are working with other number systems. You don't have to write the entire thing. You just need to write a small subset, and then from there you will be able to use any multiplication or division method to directly multiply and divide within that number system as itself, right? So for example, 2 into 1 is 2, 2 into 2, 4, no problem. 4 exists in quinary. Now 2 into 3 is 6. Now, either we say 2 into 3 is 6, or you add 2 to 4, right? 4 plus 2. We've seen how to add numbers using Shuddha process. So when you go, say 4 plus 2 here, so I write 4 and 2 underneath it, and I add in quinary. Now 4 plus 2 will become 1 and 1. So this 1, 1 is the answer. 4 plus 2 is 6, is 1 more than 5. So it has to be 1 that carried forward, and there is a 1, we drop to the next. So it becomes 1, 1. So we write 1, 1 here. You add another 2 to it, it's 1, 3. So 2 into 4 is 1, 3. You can check 1, 3 in quinary is 5 times 1 and 3, that is 8. So 2 4s are 8. It's fine. Now 3 1s are 3, no problem. 3 into 2 we already did. 11, not 11, sorry, 1 1. 3 into 3 is 9. So you have to add 3 to 1 1. So I go back to this and I add 3 at the bottom here. If I do this, I add 3, I get 1 4. No problem with that, that's easy. And then I have to add another 3. So again, under this 1 4, I add 3. So now I get 4 plus 3 is 2 more than 5. So it will be 2 underneath, and I carry forward 1. So it becomes 2 2. So then I write 2 2. Now 4 1s are 4, no issues. 4 2s I've already done earlier. That's 1 3. 4 3s is 2 2. And 4 4s are, now add 4 to 2 2. Now 2 plus 4 is 1 more than, so it becomes 3 1. So this is the multiplication table we need. If we know this, then we can now combine this with the dot multiplication method to be able to then multiply numbers directly in quinary. Now, for any system, you can do that. If you want to work to base 7, you just have to make a small table like that. and we will be able to do the multiplication. Let's see, for example, some lag from the board. I'm sorry for that. I'll try and keep it neat. So let's take 4, 2 into 2, 3, and let's keep this table handy. This one, we need this. So now if I go start multiplying 4, 2 and 2, 3. In dot multiplication, I'll make 3 parts. So this is the rightmost, then the crisscross, urdhva tiryak, as we say in Sanskrit, and then you get the leftmost. Now, if we go, now we have to remember that multiplication table. 2 times 3, here is 1, 1. So this rightmost part is 1, 1. Yeah. Then the middle part, I have to add 4 times 3 and 2 times 2. Now 4 times 3 from here is 2, 2. So I'm adding 2, 2 plus 2 times 2 is 4. And then I have 4 times 2 is 8. Sorry, 4 times 2 is 1, 3. Now to just make sure I pass properly. Now 2, 2 plus 4 becomes 3, 1. So now this 1 goes here and this 3 will go here. So we will go to this place. So what we will get is 1 on the rightmost, then 1 plus 1, 2. And then this 3 gets added to 1, 3. Now 3 plus 3 is again 1, 1. So it becomes 2, 1. That's the answer. 2, 1, 2, 1 in base 5. So without doing any conversion to decimal and multiplying, by building this table with the Shuddha, with the help of the understanding of the Shuddha. And the dot multiplication process, without changing anything, we've been able to directly multiply in base 5 and get the answer as 2, 1, 2, 1. We can do a verification with our digital roots. So if you take the digital roots of these two numbers, multiply the digital roots, you should get the digital root of this, of the answer. So as you can see here, 2, 1, 2, 1, the digital root is cancel out the 4, so I'm left with 2. I'll just remember that it is 2. Now this 2, 4 plus 2, 6. 4 and 2 cancel the 4, 2 is the digital root. Now 2 and 3, the digital root is 1. You multiply 2 into 1, you get 1. Sorry, 2. So the digital root is matching. So as the digital root is matching, the answer is probably correct. That's a quick check, quick and dirty check. Now this is a combination of all the things you have seen. The Shuddha and the dot multiplication and the digital root. We are able to quickly do the multiplication within the number system itself. You can do any more examples. I'll not do. We can do more now. Now this can do for squares within the within the number system itself. For example, 2, 2, and I'm trying to square it. So it's very. So I have 2, 2, and then 2, 2. So the 3 parts. Now 4 here. 4 exists in the quinary. Now 4 plus 4. 4 plus 4 becomes 1, 3 in quinary. And then 4. So the square of 2, 2 in quinary, sorry, it's not 5. Now when you pass this 1 here, that 4 plus 1 becomes 1, 0. So it's actually 1, 0, 3. That's the multiplication of 2, 2 and 2, 2 in a quinary system. That's the square of 2, 2 within the quinary system. So as long as we remember the Shuddha and the dot matrix and the table, we should be able to do it very easily. like that, you can try any number of examples. Now there is another very nice variation of multiplication, which is called the near-based multiplication, right? Which really leverages complements to do the multiplication when both the numbers are close to a base. When I say a base number here, the power of 10. For example, if I am multiplying 13 and 14, or not 14, sorry, 1, 3 and 1, 4 in quinary system. Now, the closest base here is 1, 0. Now, the difference to the base is 3. I write the base, the difference here 3. And the difference of 1, 4 to 1, 0 is 4. And then the answer in this technique has two parts, the right-hand side part and the left-hand side part. Right-hand side is the multiplication of the differences to the base. That is 3 into 4. Now I go back to my previous table. 3 into 4 is 2, 2. And then the left-hand side part is the number 1, 3, and you cross addition. You add like this, or the other way around. So you add 30, 1, 3, and 4. Now 3 plus 4 in quinary is 1, 2. So I write 2 and 1 is carried forward. So it becomes 2. And now this 2 has to go here to be passed through. And I get 2, 4. So it's a near-based multiplication technique. It's exactly the same technique we use in decimal system. We take the base, closest base. In this case, it is 1, 0. Now then write the differences to the base. Because both the numbers are greater than the base, you just write the differences to the base. And then the right side answer is the product of the differences. The left side answer is the cross addition of the original number and one of the difference, the other difference of the other number. Exactly the same, but every step we are leveraging the Shuddha and the multiplication table we've written. You can do, when, for example, let's say, when they are close to 1, 0, 0. Like, for example, 4, 3, 4, 4, and 4, 2. So if I go to 4, 4, 4, 2. In base 5, I'm working of base 5, the quinary. Now, if you notice the number, the base, the number closest to 4, 4 is 1, 0, 0. No, because there is no 4, 5 there. And there is no, if you add 1 to 4, 4 in quinary, it becomes 1, 0, 0. So the complement of 4, 4 rather in quinary, if you take 100 as the number, 100 as the number, and you write the complement all from 4, last from 5, you get 1. So I'm just putting a minus because it is less than 100. And for 4, 2, if you take the complement all from 4, last from 5, it is 3. It is much simpler than the previous one, if you notice that. So then the right-hand side is 1 into 3 is 3. And the left-hand side is the cross addition, right? 44 and minus 3. 4, 4 and minus 3. So 4, 4 and minus 3 gives 4, 1. So the answer is 4, 1, 3. 4, 1, 3 is the product of 4, 4 and 4, 2 in quinary. So it's a very nice application of the near base multiplication technique we do in decimal system. We've just applied it to quinary by noticing that both the numbers 4, 4 and 4, 2 are very close to 1, 0, 0. So as you can see, you can consistently apply this without going wrong anywhere, as long as you remember the small table we had. There is a very interesting application of this sutra called ekadikena purvena and antyayor dashakepi to multiply numbers when the last digits add to 10 and the remaining numbers are same. For example, 3, 5 into 3, 35 and 35. 5 and 5 add to 10 and 3 is the same. In 46, 44, 6 and 4 add to 10 and the other two 4s are the same. So in this, the way we do multiplication in decimal system, for example, if I were to do 46 into 44 using the Antya or Dashakepi Sutra. Again, the answer has two parts, the right hand side and the left hand side. 24 is the right hand side. It's the product of these two numbers. And the right side is this number 4 into the next, increase it by 1, 4 into 5. So the answer is 2, 0, 2, 4. So this is base 10. Now let's see if we can do the same in base 5. In base 5, the difference is the last digits add to 1 0 only in the language of quinary, but in the language of decimal, they should add to 5. And the rest of the digits should be same. So for example, if I take 3 2 into 3 3, this is satisfying that condition of the last digits adding to 1 0 in quinary and the remaining digits being the same. So now if I do this, the same process should apply. So 3 2 into 3 3. The right side is the product of 2 and 3. 2 and 3 in quinary, by the way. You should not forget that. So 2 and 3 in quinary is 1 1. And on the right side, I multiply 3 with 1 more than it. And which means 3 into 4. 3 and 4 in quinary becomes 2 2. This is your product 2 2 1 1 of 3 2 and 3 3 in quinary. The answer is in quinary directly. So exactly the same process as we do in decimal, Antyayor Dashakepi, ekadike purvena. So the left digit is multiplied with 1 more than it. The right 2 digits are multiplied to give you the right hand side. So that's again the process which we used in decimal has not changed. Now Dvajanka division. Now the last process I would like to show is the flag division process which we use in decimal is also applicable exactly the same way in 2 1. Now I'm not going to work out a decimal example for Dvajanka, assuming that some of you know, but I'll directly show you in the quinary system. Just bear with me while I do that. So let's say we have 3 2 3 4 in quinary, and we are dividing with 2 1 in quinary directly, and that's the objective we have to do. So I will start with 3 2 3 4. Let me draw the reminder line. As we all know, this is the reminder line. Whatever we get in the process after this is the reminder. Now I'm dividing with 2, and 1 is the raised as the flag digit. I start dividing the first digit with only 2. 3 divided by 2 gives me 2 1s are 2. 1 is the remainder. One remainder goes here as 1 0. So this is actually 1. It becomes 1 2. And then I have to do an adjustment for this 1 I did not use. So the adjustment is this 1 into the quotient number. That's the adjustment. So I get 1 1. Now 1 1 divided by 2 in quinary. If you remember this table, 1 1 divided by 2 is 3. The quotient is 3. So I write the quotient number 3. Now carry forward. And then the adjustment is 1 into this new quotient number 3. So it becomes minus 3. So the revised dividend is 0. 0 divided by 2 is 0. Now there is no adjustment because the quotient is 0. 4 minus 0. So your quotient is 130 in quinary, and the remainder is 4 in quinary. That's the result of this division. 3 2 3 4 divided by 2 1 in quinary. Now all we had done was built this small table and used the Dvajanka division, the flag division process exactly the way we do in the decimal system without any change. And we sort of landed at the result of that calculation. So this 3234 divided by 21 gives you 130 as the quotient and 4 as the remainder. You can check it as well. If you want to do the multiplication and check, you can quickly multiply here. So I'm multiplying 130 with 2, 1. 5 digits I'm multiplying, so answer will have 4 parts. So 1, 2, 3. Okay. Now the rightmost is the product of 0 and 1, so it is 0. Left is crisscross of this, 3 into 1 and 2 into 0, that is 3. Now I am doing the moving multiplier. Now this multiplier moves 1 step to the left. So it becomes 1 into 1, 1, plus 3 into 1. 3 into 2 is 6. 6 is 1, 1. So 1, 1 plus 1. So it is 1, 2. And 2 into 1 is 2. Now this 1 I have to pass. So I have 3, 2, 3, 0. And then 4 is the remainder. I add, I get the original dividend. You can verify like this. You can verify with the digital roots, digital root of the quotient into digital root of the divisor plus digital root of the remainder should be equal to the digital root of the original number. So the original number 3234, if I cross out 4s, there is no digital, it's actually divisible by 4 in quinary. So I should get 4, or I should be able to cancel out everything when I do the digital root check. Digital root check of 130, this is divisible, this is 0. So 2, 1 is 3, but 3 into 0 becomes 0 plus 4. Again, I'm adding a 4, cancel out the 4, I get 0. So digital roots are matching. So I'm able to do the division in quinary, multiplication check in quinary, and the digital root check in quinary, all done in quinary, retaining the processes as it is. So that's so we've covered addition, subtraction, multiplication, division, and squaring as well. So we sort of seen the 4 out of the 8 operations or maybe 5 out of the 8 operations in terms of how these sutras are applicable consistently across all the number systems. That's what I had to show you today in terms of some quick calcs.
Thank you so much, Sripathi. This was really interesting and a beautiful insight into how you can apply the same sutras to the different number systems. I will invite Srinivasa to give your insight into what you felt about this talk, Srinivasa. Sorry.
Yeah, thank you, Swati. Thank you, Sripada. Actually, I think I can call you Sripathi Sripada, right? So, yeah, actually, when I observed it, it's so easy, actually, how you explained it. In Telugu, we say like, aratipandu valchipettinattu. That means basically peeling the skin of the banana and giving it. So you made it so simple and it's so understandable. So I really like it. And I think everyone who joined today, they all liked it, I guess. So we are looking forward for many presentations like this going forward. Thank you very much for your time and explaining so clearly of every aspect of all the addition, subtraction, multiplication, division, and all aspects within the quinary system. And we can extend it for any base, basically, other than most of the time we teach in decimal system, but we can extend it to hexadecimal, binary, or octal system, whatever it may be. So it's so useful and going forward for the kids, actually, when they learn all these things, they really enjoy working with math like this. Thank you very much for your question.
Thank you, Srinivasa. I'll ask Prajakti, and then Rick, if you want to talk, I'll also invite you. But I wanted to ask Prajakti to give her insight into this talk and kind of say thank you from IVM also.
Yes, good evening from my side. I'm in India. So, Sripathi, Sripada, sir, I'm very much thankful for this beautiful presentation. What I observed is very logical connection between decimal and all other number system, and the flow in which all sutras are working. And I think the abstraction which is there, or the potential in sutras to do that kind of abstraction, is really wonderful. And if we teach like this, to say ninth grade or 10th grade students, the potential of switching to this different decimal system and doing operation, I think that is a very good foundation for computer science also for them when they are doing coding in the later stage. So I think this is a very nice very nice lecture, and thank you, Sripathi sir, for being with us today. It is really, we enjoyed this particular session. And actually, although you had made it very simple, I know it is not that simple actually. It is, the difficulty level and the depth level increases. I know that when we apply to more complex sutras. So thanks very much from IVM team and from all of us here.
Thank you. Thank you, Prajakta. Rick, do you want to say something? You need to unmute. Yep.
There we go.
Yeah.
No, I enjoyed the presentation, and I'm just kind of curious if you've shown these methods to younger people, taught in school or something like that. How well was it received? At which point, above which point were the kids getting it? Below which point were the kids having problems with it? Like third grade, fourth grade, eighth grade. What's your experience been with showing it to children?
This is probably 9th grade, 10th grade, children will get it. I mean, if they are introduced, I mean, at least when we studied, we used to study different number system problems in 8th, 9th, 10th grade, somewhere in that period, we were introduced to quinary systems and, the septa system, etc., and hexadecimal system, etc., right? We used to have this kind of problems, like Prajakti said, it's very, I think it is very important for students who want to study computer science or mathematics, higher mathematics, because what if you notice the sutras and carefully abstract, you can actually abstract an algebraic notation against, behind each of these, processes, right? So it's basically how numbers work. So you could notice the process, and then when you go to degree maths, and my elder daughter comes back and says some of these, we are discussing in degree maths, in the first year math as the abstraction of the process. The discussion is about the abstraction of the process, right? Not necessarily the sutra, but the understanding of the sutra definitely helps. Maybe 9th grade, 10th grade is what I think this will be interesting, in terms of applicability across number systems.
I know when I first started studying computer science, making the transfer from decimal to binary, it wasn't trivial. Maybe on addition it was trivial, but you get into multiplication and division, it was not trivial.
Correct.
And this makes it a lot simpler.
Yeah.
And I mean, call it whatever you want to call it. It's a method that works.
Yeah.
And I congratulate you. It's you showed some great insights in putting this presentation together. Thank you.
Yeah, basically it's a Boolean algebra we use a lot in computer science. So where you can convert hexadecimal to binary, the other way, and octal to binary. So many concepts. This is very, very helpful in those areas.
Thank you so much. Yeah, thank you. And there's one message for you. Thank you for sharing the sutras. I do hope for more sutras to be explained, especially to us who are beginners in Vedic maths, more power. I do understand it was a lot of information for people who were not introduced to Vedic mathematics, but we do hope to get more workshops kind of things bringing to you, where we would have a more in-depth understanding of Vedic maths and then applicability to the different number systems. That's definitely what we would plan after this. And that's what I was thinking as this webinar was going, that it needs to be a more hands-on workshop also for people to practice. But this was a great introduction. Thank you. Thank you so much. And we hope to keep seeing you again. This is not the last time that this audience is going to see you. And before I close, I just wanted to make a couple of announcements that are coming up with at IAVM. The first one is about the online conference. The first one is about the online conference that's coming up on June 10th and 11th. We have sent out the call for papers. In case anybody who is in this audience and have not received this flyer about call for papers, please reach out to us at instituteavm@gmail.com. Please share it with your friends, colleagues. The last date for the abstract submission is 2nd of May. We invite you to submit your original research paper on Vedic maths application, Vedic maths in education, or ancient Indian mathematics. Also, we invite you to talk about your Vedic maths story as to what inspired you to study Vedic maths, why are you continuing studying Vedic maths, or any of your successful initiatives that you think you can share with the larger audience. And last but not least, even if you're not able to send this, please join us on June 10th and 11th for the conference. This is our 9th online conference, and we do hope to see all of you there. And another competition that I wanted to talk to you was about the Lilavati contest. The Lilavati contest, we're hosting this for the 3rd year in row. Here we're inviting you to submit a poem, a rhyme, or a riddle involving math. We have 4 categories, and the last date for the submission of the entries is 12th May. So please, and again, if you haven't heard of either the online conference or the Lilavati contest and would like to know more, or just reach out to us at instituteavm@gmail.com, and we will surely respond to you. So again, thank you everyone for joining us. And last but not least, do not forget to like our Facebook page, because you'll get to know more about our upcoming events, initiatives on that page. Thank you, everyone, and hoping to see you all soon. Thank you.
Thank you.
Thank you. Take care.
Thank you.